Good morning, students. Till now, we discussed the dipole and the different cases. All those things we discussed in the last class. Now, we'll go for the another example of electric field intensity related one problem. That is, charges, if charge Q is at located at 1 centimeter, 2, 4, 8 centimeters and so on. Charge Q is located at 1 centimeter, 2 centimeters and 4 centimeters and so on the x-axis. Then the electric field intensity due to these charges, then the electric field intensity due to these charges at origin is how much? Means you can understand that yes, a charge Q we are locating, that may be 1 coulomb or 2 coulomb, so that is different. So they are locating at 1 centimeter, 2 centimeters, so on, etc. Along the x-axis. Then those charges will exert electric field intensity. So what is the electric field intensity at the origin due to these charges we need to be calculated. So this is also the standard example. Now you take the coordinate system like this. So x, y. So here this is origin. From origin, first the charge is located at 1 centimeter. So this is Q, 1 centimeter. Next, the charge is located at 2 centimeters. So next charge Q is located at 2 centimeters. Next charge Q is located at 4 centimeters. Next charge Q is located at 8 centimeters and so on. Then every charge will be exact, so produces electric field at the origin. So the charge of 1 centimeter will be produces an electric field intensity that is away from it, because of it is a positive charge. Electric field intensity away from it, that is E1. Similarly, the charge which is at 2 centimeters also will exert electric field intensity, will produces electric field intensity, that is E2, away from it. Like that, what happens here, the electric field intensities due to these charges all are in the same direction. Then we can say the resultant electric field intensity is the summation of all these electric field intensities. Then ER equal to, then the resultant electric field intensity is, then the resultant electric field intensity E equal to sum of all these. What about E1 here? E1 in the sense K. E1 is a cells K 1 upon 4 pi epsilon naught. You can write as a K Q by R square. R square means 1 square, 1 centimeter square. So 1 centimeter square in the sense 1 into 10 raised to minus 4 we can write. Because 1 centimeter in the sense 10 raised to minus 2 meter. So 1 centimeter square means into 10 raised to minus 4 meter square. Like that, E2 is K into Q by 2. 2 square means 4 into 10 raised to minus 4. Like that we will get. Then all these if you added, so same way here E3 in the sense K into Q by, so 4, 2 square, next 4 square, 2 square, here 4 square into 10 raised to minus 4. Like that it will come. So I am writing the total electric field intensity in the sense that is E1 plus E2 plus E3 and so on. So E1 plus E2 plus E3 and so on. Then E1 is nothing but here E1 is K q by charge is q, kq by 1 square into 10 raised to minus 4 plus E2 means kq by 2 square into 10 raised to minus 4 plus kq by E3 in the sense 4 square into 10 raised to minus 4 plus kq by 8 square into 10 raised to minus 4 and so on. Infinity, up to infinity it is there. Then common, if you take common outside, then k into q, and also here 10 raised to minus 4 if you take common, 1 by 1 square 1 plus 1 by 2 square, 1 by here 2 square whole square, so 2 power 4, here 2 cube whole square 2 power 6 and so on, it will come up to infinite terms. So this is what sum of infinite terms here. So sum of infinite terms means the s infinity, sum of infinite s infinity we need to be find it out. This is first term and this is second term by first term is called common ratio. So first term is, we can take it as a and second term by first term is called as the common ratio r. So we can write here, this is the sum of infinite terms, sum of infinite terms. Then we can write as, so sum of infinite terms in the sense we can write as here first term a equal to 1 and common ratio r equal to t2 by t1, t2 by t1 in the sense 1 by 2 square by first term is 1 and it is 1 by 2 square in the sense 1 by 4, common ratio. So sum of infinite terms is s infinity, so s infinity is equals to a by, so 1 minus r. If r is less than 1 means 1 minus r, if r is greater than 1 means r minus 1 you will get. Here 1 minus r. Then a is the first term 1 by 1 minus r is 1 by 4. Then it will be, so 3 by 4 means 4 by 3. Then completely we can replace it, that one. Then electric field intensity equal to, outside we have q by 1 kq by 10 raised to minus 4. Completely s infinity we got it as 4 by 3. Then we have k q by 3 into 10 raised to minus 3. So then you can write k value 9 into 10 power 9, 9 into 10 power 9 into 4q by 3 into 10 raised to minus 3. Then it will be 3 3 is 3, 12, 12q. So for 12q into 10 raised to 12, 12q to 10 raised to 12 Newton per coulomb. Here if they give q equal to 1 coulomb, you will get 1 coulomb in the sense 12 into 10 raised to 12. 1 microcoulomb, 1 into 10 raised to 6. Like that, whatever the charge they give, equal charges, that charges you have to be substitute here. Then you will find the electric field, total electric field intensity. So this is the case of different cases already we discussed in electric field intensity problems. So that is you have to be practice it. Next we can go for the, till now we have discussed that discrete charges, the point charges are as in the form of discrete charges. So next we will go for the continuous charge distribution. So now continuous charge distribution. What is continuous charge distribution? Till now we discussing that only about the discrete charges in the sense point charges. So till now we discussed only discrete charges, that is q1, q2, etc., qn. If point charges are there, those we can apply, means that we can treat it as a discrete charges q1 q2 like that. But if the charged bodies means if a straight conductor is there like this, so straight conductor is there like this, it has a charge. So this kind of charged body we cannot treat it as a point charge, either like q1 or q2 like that, we cannot be treated. Or else if you take a sphere, so if you take a sphere, so it has a charge over it, then this is also we should not be treated as a point charge. Like that if you take a cylinder, so this case also here the charge is distributed over it. So this is also we cannot be treated as a like discrete charge. Here completely the charge is distributed over the body. So not only surface, if insulating material is taken, charge is also present inside it also. So such kind of bodies are there. We instead of treating that, so instead of treating the point, these charges are point charges. So we will be go for a continuous charge distribution. Here you see this is the first body you observe it. Here the charge is linearly distributed along the lengthwise. The charge is distributed. And here if you observe surface, along the complete surface the charge is uniformly distributed. Similarly, if you take the cylinder, if it is a non-conducting, I will tell you about that non-conducting and conducting. Okay, so first you just you understand now, we'll be discuss about this. Non-conducting means the charge will be completely present inside and as well as on the surface. This kind of body is there completely throughout the body what charge is present. So lengthwise charge is present, we have to take linear charge densities, surface wise charge distributed equally surface charge density, and volume completely throughout the body charge is distributed, we'll go for the volume charge density. Because those densities, if you know, if you want to find the electric field intensity, due to a small amount of length, due to a small amount of area, due to a small amount of volume, we can able to calculate the charge first, then we can able to integrate it, you can able to find the total charge is present over the surface. So that is the one of the method. So you observe here charge linearly distributed means we'll go for linear charge density. Charge surface wise distributed means we'll go for the surface charge density. The charge is distributed completely throughout the body, in the sense we'll go for the volume charge density. Like that we have different kinds of charge densities based on the distribution of charge over the bodies. So that's why now we'll go for the different charge densities. So based on the distribution of charge on the surface of the body, based on the distribution of charge on the body, based on the distribution of charge on the body, we have three kinds of charge densities. We have three kinds of charge densities. One is linear charge density, lambda. Second one is surface charge density, sigma, and the third one is volume charge density, rho. Like that we have three kinds of charge densities. First, linear charge density. Linear charge density, lambda. the charge is distributed along the lengthwise, the charge is distributed along the length, then we can say that then we can go for the linear charge density. In this case, if the charge is distributed along the length, the charge is distributed along the length, we can go for the linear charge density. Linear charge density lambda is nothing but charge per, we can write as a charge per unit length. Let us take here a linear conductor AB. So this is having completely this body having some charge over it. So this is having charge. So in this, if you take a small element, this is completely length is L. In this, if you take a small length element dl and it is having some charge q, so this small length element, how much charge it is having means, so that L charge we took as a delta q. So the entire conductor length is L, that is having some charge q. In that, if small length element, if you taken that small length element, how much charge it is having means a small charge dq, then according to it, this conductor having a linear charge density lambda means lambda equal to, we can write as a dq by dl. From that dq equal to, we can write linear charge density into delta L. So this is the charge of small element, but if you want to find the charge of this entire conductor means you have to integrate it on both sides. So integral dq, if you taken integral dq is equals to integral lambda dl, therefore q equal to integral lambda dl. Like that you can able to find what linear charge density. So linear charge density means charge per unit length. If you have linear charge density of a conductor, if you want to find the charge of that conductor means, so charge equal to linear charge density into length. Remember it. If you know the conductor linear charge density, charge of the whole body, if you want to know it, that is the linear charge density into length, you have to be multiplied. And the lambda units here, lambda units is coulomb per meter because charge by length. Next we can go for the surface charge density. Surface charge density sigma means, if this case, if the charge is distributed over the surface of the body, then we'll go for over the surface of the body is there charge uniformly distributed means, so then we'll take surface charge density sigma. So if the charge is distributed over the surface of the body, the charge is distributed over the surface of the body. So sigma we can write as a charge per area. So over the surface means charge per unit surface area, will take it. So units are coulomb per meter square. Suppose if you have a surface like this surface is total surface area is S. So this surface area is on the surface area, the charge is distributed uniformly throughout it. The charge is distributed uniformly throughout it. And this, if you have taken a small area like this, so this small area having area vector ds. So complete area is having charge q and having surface area s. This small area, so this charge density is sigma, if you know. So if you this small area, how much of charge it is having, how can you find? This is a charge, let it be dq. So the charge of this small pot in the sense that is, you can write as a sigma equal to what we know, charge per unit area, charge dq by area is ds. From this this part, the small part, how much charge it is having, dq equal to sigma ds. Then from this, if you want to know the total charge in the sense integral, not integrate it on both sides, integral dq equal to integral sigma ds. Then q equal to, we have integral sigma ds. Like this you can able to find out the charge of the small area. Next you can find the volume charge density. Means if the body, third one, volume charge density, volume charge density. So volume charge density will take as a, so rho. So volume charge density in the sense what we have here is if the completely throughout the body, if the charge is distributed, so if the charge is distributed completely throughout the, if the charge is distributed throughout the body, we will take it as a volume charge density. So that volume charge density, how can you determine? Here is this rho we can define as charge per unit volume, and charge per unit volume in the sense it is coulomb per meter cube is the unit. Suppose if you have some spherical some body, so one body is there, so through this body, it is not surface, it is a three-dimensional body. If this body having charge, and the charge is uniformly distributed, and this charge density of this body is rho, we know. So in this small volume part, if you are assumed here, if you taking a small volume part here like this, small volume part if you are taken, that this volume is dV. So this volume, how much of charge it is having, we don't know how much charge it is having, that is we are taking as a dq. According to this definition of volume charge density, rho equal to what you can write, rho equal to dq by dv. So rho equal to dq by dv, from this dq equal to what you can write, rho dv. And if you want to find this charge having, so charge contained in this volume part, that is if you want it, so you can write like this. If you want to find the charge of this entire body, so entire body charge, if you want it, what you can go for the integration on both sides, integral dq equal to integral rho dv, then q equal to integral rho dv. This is the total charge. Like that we have volume charge density and the surface charge density and linear charge density. Lengthwise charge distributed linear charge density, surface wise charge distributed surface charge density, and volume wise charge distributed volume charge density will be taken. Now few of the cases which are useful for entrance examinations, those results directly will be discussed. Those derivations we no need of it, because those derivations are very lengthy, so we need only the some results directly will be discussed it, and those cases which are useful for entrance examinations. So now we'll go for it, objective purposes which are useful based on the charge distribution, those will be discussed. Then we can go for the another important last concept, Gauss law, that is very important. Before that, some few results which are useful for objective purpose will be discussed it. First one in that, this is only for entrance, okay, entrance purposes. First one, the electric field intensity due to a straight conductor, the electric field intensity due to a straight conductor of length L and charge density lambda at a distance r from the conductor. A distance r from the conductor. Let's take a conductor which is a straight conductor like this. This conductor, the charge is uniformly distributed, and this charge density they given as lambda. So from this conductor at a distance r, so I am taking a point P, and this conductor whole length is L. Whole length is L, and linear charge density is lambda. So here the case is, due to this conductor, what is the electric field intensity at this point? If it is a positive point charge, means one single point charge Q, means here directly you can tell that the electric field intensity direct formula we already discussed, that 1 upon 4 pi epsilon naught into Q by distance r square. But it is not a point charge, it is a charge uniformly distributed over the length, continuous charged body, continuous charge distribution body. So this you should not treat as a point charge. Then at the time how to solve this kind of case means, here we discussed, just we have to consider a small part of it. Let us total in length L is there, no? So in this I am taking a small part of it, a small length dl I am taking, and this charge is dq. So this part charge can be treated as a point charge because we are taking only infinitesimal small charge. This is, you can treat as a point charge. Due to this small point charge dq, here electric field intensity means you can write formula that 1 upon 4 pi epsilon naught dq by distance from here to here. Okay. So now I am taking that. So let us just discuss like this. This element I am taking here at a distance x from the charge, and I am taking a small element dx, you take it, okay, small element dx from point P at a distance x. The small element charge is dq. So the small element charge dq, in the sense due to this small element dq, here the electric field intensity is not by the whole conductor we are finding the electric field intensity due to this small element. The electric field intensity is not total one, it is a small part of the conductor only. That's why the field due to dq at P is, it is not complete field, so that's why dE, that is dE equal to, we have 1 upon 4 pi epsilon naught. So what is the charge now? dq by what is the distance here? X square. But this is not the complete field, but we want to find the field due to this entire conductor. Entire conductor in the sense starting from length r to this end will be what? R plus L. So from starting from R to R plus L, if you integrate this one, you will get the what? Total charge body. Totally this charged body you will consider. So you have to integrate it on both sides. So within the limits of starting, this end will be at R distance from P. This end will be R plus L distance from P. That's why integrating on both sides to find the total field. To find the total field, what I am going to take here, integral dE is equals to integral from where to where I am taking, from first end R to second end R plus L. So 1 upon 4 pi epsilon naught dq by what here dq by x square. Here dq, the given linear charge density. So we know linear charge density is nothing but charge per unit length. So dq by what is the element length? Dx. Okay. Then dq equal to, we can write what? Lambda dx. That if you write here, this expression is how it is going to become. Integral dE means total electrical intensity E, and R2 R plus L 1 upon 4 pi epsilon naught into dq plus this dq plus we will write what? Lambda into dx. So lambda by x square into dx will come. So I am writing that here. So we can write as lambda. So integral dE is dE equal to integral R2 R plus L. So 1 upon 4 pi epsilon naught dq in the sense lambda into dx by x square. So lambda by 4 pi epsilon naught is constant. Now how lambda is linear charge density, it is for this conductor it remains constant. Then we have 1 by x square dx, limits are from r to r plus l. 1 by x square means minus 1 by x integration here, lambda by 4 pi epsilon naught. So 1 by x square means minus 1 by x integration, limits are from r to r plus l. Then if you reverse the limits, minus will eliminate. So lambda by 4 pi epsilon naught, I am writing that 1 by x, limits are from r plus l to r. Then if you substitute, apply the limits, first upper limit minus lower limit, then lambda by 4 pi epsilon, then 1 by r minus 1 by r plus l. This is what we can say as the electric field intensity due to a linearly charged conductor at any point distance r from one end. So this is the electric field intensity along axial line. Now we have another case that if a finite conductor is there, normal to its conductor, what is the electric field intensity at a distance r? So here the another case I am going to take, second case. If a conductor is there like this is the a linearly charged conductor, and this conductor, from this conductor along axially we took here at a distance r, how much we have. Now it is normally like this at distance r. Here what is the electric field intensity, we have to know it, and this linear charge density is lambda. Here these are the derivations and all we won't be do directly. You can take the result. That is only important to us to you can remember these derivations and all, we no need of it. So I am taking, this is finite conductor. Finite conductor means here at a distance r from this conductor normally. So at a distance r from a conductor normally, normal to it. Finite conductor, this end, the lower end, it is making an angle theta 1 here. If this exactly this point I not took at the midpoint, that's why lower end makes a different angle, upper end makes different angle. So this end making an angle theta 2. That's why here upper end little bit more. So if you are not able to see clearly, that I can understand little bit large. If you taken, so this angle is theta 2, this angle is theta 1. Here more charge, less charge. Because of more charge, here we have two kinds of electric field intensities. One is along x direction Ex, and along y is downwards here, because of majority of charge, more charge here it is present. If you take down here, more charge is there, then it will be electric field intensity along y-axis downwards. But if you take up, then electric field intensity will be along positive y-axis side. Now here it is Ex and this is Ey, electric field intensity along y-axis. What about these Ex, Ey? Okay, so what about these Ex, Ey, where theta 1 is the angle made by the lower end, theta 2 is the angle made at the upper end at this point P. Then here the electric field intensity Ex is equals to, so lambda by 2 pi epsilon naught. Here we have the result that, so lambda by 4 pi epsilon naught r naught into, we have a result that lambda by 4 pi epsilon naught r into Ex in the sense sine theta 1 plus sine theta 2. Theta 1 is this one, theta 2 is that upper one, theta 2. Similarly Ey, so Ey is nothing but lambda by 4 pi epsilon naught r into cos theta 1 minus cos theta 2. So these results you can remember along Ex in the sense that is sine theta 1 plus sine theta 2, lambda by 4 pi epsilon naught r, and Ey in the sense lambda, where lambda is charge per unit length, linear charge density. So lambda by 4 pi epsilon naught r into cos theta 1 minus cos theta. You can understand here lambda is the linear charge density of the conductor, and theta 1 is the lower end, what is the angle made by it, theta 2 is the angle made by the upper end, and r is the distance from the conductor. So this is the formula for finite conductors. But if the case, if it is an infinite conductor, what happens? So infinite conductor means what is the result that we need to be discussed. So finite in the sense result, you remember it. Based on this we can different cases can be arise here. So infinite conductor, what is the electric field intensity? Even in infinite conductor at one end, what is the electric field intensity? Those formulas we can discuss it. Now from these subcases, what are the subcases here is, let us take if infinite conductor is there, in case of subcases, in case of infinite conductor, infinite conductor means the conductor so infinite conductor is there. In this infinite conductor, we are taking at a distance r. Here electric field intensity. So infinite conductor in the sense earlier finite conductor means angle made like this. So here theta 2, this end theta 1 you took. But infinite in the sense this infinite is like this, continuously downwards, it is continuously upwards. Then what is the angle made by the infinite conductor at this point P? You observe this point P, infinite in the sense where we can see like this. So infinite conductor in the sense this angle will becomes what infinite in the sense this angle is becomes 90. Similarly downwards, so this angle is infinitely down in the sense this angle is becomes 90 like this. Then here at this point P, the theta 1. So this theta 1 becomes 90 degrees, theta 2 becomes 90 degrees. Theta 1, theta 2, 90 equal angles means we have the result, no? So according to formulas already we discussed, lambda by 4 pi epsilon naught r. What is the formula along Ex in the sense sine theta 1 plus this is Ex and this is Ey. We took sine theta 1 plus sine theta 2. Here theta 1, theta 2 both are 90 degrees. Then we have the result lambda by 4 pi epsilon naught r. Then sine 90 plus sine 90 in the sense 1 plus 1. Then it will be lambda by here 2, here 4, 2 times cancelled, then lambda by 2 pi epsilon naught r. And along Ey in the sense we have lambda by 4 pi epsilon naught r into cos theta 1 minus cos theta 2. But here cos theta 1, cos 90 minus cos 90, anyhow cos 90 0, so totally it will be 0 only. So what is happened here, only infinite conductor is there at a distance r. We have only electric field intensity along x direction. That is how much here, lambda by 2 pi epsilon naught r. This is the result. If second case, you can take that this is only along y direction electric field intensity 0, only we have along x direction electric field intensity, that is lambda by 2 pi epsilon naught r. Along y 0. Next we can go for infinite conductor one end. So very long conductor is there, one end if you taken. So second case 2 here. In case of infinite conductor at one end. So at any one end if you're taken, we have the result like this. So this is the like it is a infinity conductor, but other end we are having one end, and it is we are going to take at one end in the sense here what is the electric field intensity distance r from one side end, and is along vertically it is up to infinity it was there. Then one end if you taken, so we have the case that here if theta, if this r if you taken down, this theta becomes what, 0, because this r if you taken down in the sense theta 1 becomes a 0. So that's why here you can observe the theta 1 is in this case the theta 1, because r what you one end if you taken, this lower end at this point makes what, 0 angle. So theta 1 is 0. But theta 2 in the sense it is up to infinity it is there. Infinity in the sense what is the angle made by it? Here the angle made by it is theta 2 is 90 degrees. Theta 2 90 degrees. Therefore these things if you substitute in the expressions, theta 1 is 0 and theta 2 is 90, then according to the expressions Ex, so Ex and Ey. So Ex is, that is lambda by 4 pi epsilon r sine theta 1. Theta 1 is sine 0 plus sine 90. Sine 0 0, sine 90 is 1. So you have Ex equal to lambda by 4 pi epsilon naught r, and Ey. So Ey is lambda by 4 pi epsilon naught into cos theta 1. Cos theta 1 means cos 0 minus cos 90. Cos 90 0, cos 0 is 1. So you have Ey equal to lambda by 4 pi epsilon naught r. Like that Ey, Ex both are there. Then you can write this as E resultant electric field intensity E equal to Ex I cap plus Ey j cap, and magnitude if you want it here. So then this resultant in the sense root over Ex square plus Ey square. Then Ex in the sense we can write as a E resultant electric field intensity in the sense root over Ex square plus Ey square. Then you will have both are same. You observe here Ex and Ey both are same in magnitude. So under root of this one in the sense, so you will get root 2 times the lambda by what 4 pi epsilon naught r. This is the result electric field intensity at one end of the infinite conductor. Like that exactly finite conductor at the midpoint. Also you can take it that finite conductor exactly at the midpoint. So case 3 here, finite conductor exactly at midpoint due to a finite conductor from the midpoint, if you taken, you are not taking infinite here, you are taking a finite one. So finite one, but you are taking exactly from the midpoint of the conductor. So exactly from the midpoint if you taken, midpoint in the sense the lower end as well as the upper end makes what equal angle, that is theta 1 is theta, theta 2 also be theta. So theta 1 theta, theta 2 also be theta. Then here electric field intensity along x direction and electric field intensity along y direction. You know Ex in the sense lambda by 4 pi epsilon naught r sin theta 1 plus theta, sin theta 2 also be theta. Then you have here lambda by 4 pi epsilon naught r into 2 sin theta you will get. So if it is 45 then 2 sin 45. So then you can get the result. Like that what is the angle 30 if they give sin 30 you can take it. So that is based on the angle you can able to obtain the result here. Like that Ey if you taken, so lambda by 4 pi epsilon naught r and cos theta 1 cos theta minus cos theta 2. So both are same angles in the sense the result will be 0, because what is the electric field produced by the lower end and electric field intensity produced by the upper end, both are equal and opposite, they will be cancelled each other. So you have only Ex. Therefore resultant is that is Ex only, that is 2 sin theta into lambda by 4 pi epsilon naught r. This is the result due to a finite conductor at one end. So like this we have circular ring is there. Due to charge circular ring along its axis, what is the resultant electric field intensity? Due to charge disk, what is the resultant electric field intensity? So those cases we need to be discuss it. So as well as arc shaped conductor is there, what is the electric field intensity? Those cases will be discussed in the next session. So next we can go for the Gauss law and its applications.